Hello YouTube, and welcome to another episode of Some Rusty Chess. In this episode we're going to look at FEN strings, which is a type of notation used to denote a given board position and whose turn it is and who can castle and things like that. It's basically representing the current state of the game. That will be useful when we want to pull in games from other sources and when we want to initialize the board in a particular position. Now, in the last episode, I kind of severely underestimated the recording time, and in the future, I'll try to make the episodes quite a bit shorter. So, with that in mind, let's get into it. So, let's first have a look at what FEN strings are. So, FEN stands for Forsyth-Edwards notation. And if anything is unclear in my explanation, you can go to Wikipedia and read more about it. So there's a bunch of adjustments, as you can see here, for different variants of chess, but we'll just use the standard one. And the standard FEN strings looks something like this. So the first thing to notice that you have these different letters, and as you may know from standard or other chess notations, then for example, R usually stands for rook, and N stands for knight, and Q stands for queen, and so on. And since this is just a plain text string, there's no simple way to denote color, and the way that color is denoted is that black pieces are written in lowercase and white pieces are written in uppercase. So small n is a black knight, and a large capital P is a white pawn. The next thing you will notice in this here first part of the string is that there's a bunch of slashes, and the content before each slash corresponds to a row. So if you look at this position, which is actually this FEN string, this first letter denotes, so the first part before the first slash is the first row, the second part before the second slash is the second row, and then so on. So this R denotes that there's a rook on the first square, which is indeed correct, and so on. Now then we get to this row, which is here, you can see it's the third row, so it corresponds to this, and it just has the number 8. The reason for that is that whenever there's an empty square or some number of empty squares, it's just denoted by a number. So in this case there's 8 empty squares, so we just write 8, and then the next one is 8 again, and so on. It gets a little bit more interesting if there's not a fully empty row. For example, if you play e4, so you move this pawn to here, then the fifth row from the top becomes 4 empty squares, this one, this one, this one. I hope you can imagine it. Then a pawn, a white pawn, so you can see here, and then 3 empty squares. So that's the first part. So one of the problems we will solve is to loop through each row indicated by this string and set up our game struct accordingly. Now, so that's the first part, and then there's a space, and then the second part of the FEN string. This letter simply denotes whose turn it is. So W for white and B for black, which is pretty simple. Then the third part of the string denotes castling rights. So here, for example, a capital K means that white is still allowed to castle kingside, and a capital Q means white is still allowed to castle queenside. And similar for the lowercase letters, just denotes black's castling rights. Then the fourth part of the string is either like a dash, or it's a square indicator, and this indicates where you are allowed to do an en passant capture. So for example, in in this position, because this is just the one move, e4, the pawn moved here, then if there were a black pawn either here or here, then you would be allowed to make an en passant capture to e3. That's why it says e3 here. Okay, and the last two parts are clocks. The first one is the half move clock. Which is the number of half move since the last capture or pawn advance. So here, because we moved the pawn, it's still 0. It's used for the 50 move rule, as you can see here, which is that there's a draw if 50 moves have gone by without a capture or a pawn advance. And then the last one is the full move clock. It's the number of full game turns that have occurred. So for example, so that means that every time both white and black have moved, it goes up by 1. Alright, I think that's it for FEN strings. So now let's try to write some code to read these guys. Alright, let's get into it. So I'll just keep the Wikipedia page over here as a reference. And the first thing that we're gonna notice that if we take a look at our game struct from last time, here it is. We only have a recording of the pieces. So for each piece, where is it? And the squares, which is like for each square, is it empty or does it have a piece? But there's so that's basically number 1 over here. But we also need to store the active color, the castling, availability, en passant, and so on. So to do that, we need to add some extra fields to our struct. And let's start with the active color. It's quite simple. It's just a color. And then we need the castling rights. Whoops. So we'll make a new type for that. Then it's en passant. So as we saw down here, it can be either nothing or it can be a square. So it's quite natural to use the option type, which denotes either a no value or a particular value, and the value should be a piece position, the type we defined for, which is basically just a bit string. And then there's the half move clock. So you can just put it as usize and then the full move number. That's it. Whoops. So let's start with the active color is already defined. So let's look at the castling rights. And if you're coming from like a C style language, then it's quite natural to use a bit flag. So something like white king side is a 1 bit in the 0 position, and white queen side is a 1 bit in the 1 position. So like something, so we have 4 different types of castling rights, so we need 4 bits. So then you could write it like this, and okay, a little bit annoying Emacs. And the black king side could be like that, and the black queen side could be like that. And the reason you want to use bit flags is then you can easily make a situation where you have multiple. So for example, let's say that black had castled. That means black has no castling rights. The first 2 are 0, but white hasn't castled or moved any rooks. So both of the first 2 bits would be 1, and that would be expressed like this as a bitwise OR. So bit flags are quite natural and nice to use for this. Now, unfortunately, it's not so easy to use not as easy in C as in C at least, to use bit flags in Rust. And we kind of need to use another package. And that package is called bit flags. And with that added to our cargo.toml file, we can just use it in the top. And if we go back to our game struct, then we can add we can make a bit flags type like this using a macro from this package, and then the syntax for it is this. So we just need 4 bits, but I'm not sure there's a 4-bit type in Rust, so we'll use an 8-bit. So first of all, there can be no castling rights. We'll use a 0 for that, and then it can be a white can castle on the king side. As I said before, we'll use a bit in the 1 position, queen side, black king side, black queen side, and then we can write all as well, like this. And there we have it. Now we basically have a castling rights bit flag where we can do things like, say, castling rights dot white king side and castling rights dot black king side, and that will be a valid value. So now let's try to make the code compile, which, as you'll see in a little bit once it's downloaded the files, that it won't compile because we've added these new fields to the game struct, but they are not in the init function that we wrote last time. So let me try to compile it again. So you can see here in the error message, missing fields, active color, blah blah blah. So let's go to line 132, and we will add the fields. So when we initialize a game, the active color should be white. The castling rights should be all. The en passant should be none. The half move clock should be 0. The full move number should be 1. That's it. Now should hopefully compile. It compiles and runs correctly. Alright, so now that we have it compiling, let's start writing the function to read the FEN strings. And put it down here in the bottom of the implementations of the game. So it should take a string reference and it should return a game. And let's just make the default value like this. Then we return the game at the end. So the first thing we notice that if we try to compile this, the compiler will give us a warning that the method doesn't have a snake case name. You can see that here. So we can remove that warning by annotating it like this, and it compiles again. So let me remove that. Let's put the output of the compile over here. Good. So now we're going to be taking in strings that look like this. Let's take an example, put it down here. Not like that, like this. And a string like that, and we'll take it in and pass it. So to do that, it would be nice to define a split on function. So we can say, take the string and split it on the first slash, and give me the first part and the last part. And then we do that a bunch of times, and then we can say, now take the string and split on a space. Give me the first part and the last part, and so on. So probably there's other ways to do this, but it's just how we'll do it for now. So define a split on function, which takes a string reference, a separator character, and it returns the first part and the rest. So if we take an example, s equals a, b, c, d, f, and separator is c, then we want to return a reference to a, b, and d, f. So we'll drop the separator explicitly because when you have something like the FEN string, which is like something like this, we're never really interested in the separator character, so we'll just drop it. All right, so we can do that. Implement this function by looping over all the characters. I think we can do it like this. And if the item is equal to the separator, then we will return a string slice. And now by +1 we explicitly drop the separator and return the rest of the string. And if we never hit the separator, then we'll just return the full string and an empty string reference. So let's try to see if that compiles. All right, compiled. Let's try it out. Call it first row and rest. Split on string, and we want to split on a slash. Then we can say first is equal to that, second is equal to that. Let's comment this out for now. Okay, and that seems to be working. So now that we have that, we can start implementing the readFEN function. And the first thing we want to do is to get the position string and then the remainder for use later. And we split the FEN string on a space. Because if you look at this example down here, the position or the location of the pieces is indicated by the first part of the FEN string everything before the first space. So if we do that, it will look like this, that you see over on the right, that if we split on the space, we get the whole position. Okay. Now, once we have the position, we want to loop over each row. And one way to do that is to call the split n function that's defined on strings. And I have to put an 8 in. I think it denotes how many pieces you expect. And then we have to put a function that decides when to split. So we want to split whenever characters equal to a slash. And that will give us each row. So let's try to just check that this works. So we'll say let game equal to read FEN. Then we will comment this out for now and run it. Oops. I'm too used to... Okay. That worked. So now ideally we want to say something like give me the pieces and the squares, and we'll from this row, and maybe we need a reference. And then push all those pieces to the game and push all the squares to the game as well. Now, a problem we kind of immediately run into is that we will loop over the rows in the wrong order. So if you recall, we have kind of set it up so that this square is the 0th square, and this is the first and second and so on. But when we read the FEN string, the first square we get is this one. And the way that we handle that is by inserting the squares in the opposite order that we get them in. So instead of pushing to the end, we would want to insert from the start. So as far as I remember, there is a function to insert in the beginning of a vector, but just for fun, we could also use the deck data class for vecdeck. A deck is a data structure where you can insert efficiently both at the start and the end. So it's just what we need for this. And the deck is then used in the following way. If we go down to the function, let's make a deck that contains the squares. Then instead of pushing to the squares, pushing to the end of the squares, we push to the front of the deck. And then when all the squares have been added, then we just convert the deck into a vector and assign that to the game object. So what we need now is to implement the pass row function. So it will be a little bit complicated because if you recall, the squares need a reference to the piece, if there's any piece on them. And we also want to know what is the position of the piece. So we have a little bit of state that we want to take care of. And the way I came up with solving it is like this, which works. You can always refactor it yourself if you have a better idea. So the function gets a copy, so any modification that the function does will have no effect out here, so we have to take care of that ourselves. Actually, I'm not sure I need the piece index, but we'll see. And every time we've handled a row, we go 8 squares back from where we started. That's why we have this one. And every time we add a piece, of course, we increase the piece index. So let's now try to write the parse row function. Actually, we probably don't need. Yes, we need mutable. So this means that we are able to mutate the local copy of the indices. So we want to return a vector of pieces and a vector of squares. We may do some optimization later, but for now this is fine. And the squares in here also have to be made in the opposite order to get everything to line up. So with that in mind, we also use a deck here. And let's now loop through all the characters of the row. And we can determine, we need to know whether the character is uppercase in order to decide whether it's white or black. So like this. If it is uppercase, let me zoom in. If it is uppercase, then it's white, else it is black. Then we can write code like this. If it's an R, then we need to do some stuff. We need to make a piece which has the correct color. We need to make give it the right position. And the right type, which in this case is a pawn, a rook. We want to make a square, an occupied square. And then add those objects to the accumulator lists. And then increment these bookkeeping values. So now we could, for example, say, okay, if it's a knight, then we basically need the same code, except we write knight here, and so on for bishop, for queen, and whatever. So all of this duplicated code indicates that maybe we need to make a function or something, but actually here let's use a local macro. So a macro is a function that's running at compile time and just inserts code. And it needs to be local because I wanted to access, for example, the color variable and things like that, which makes sense now. So the only thing that's changing between all of these code blocks is the piece type. So we'll take that as an input to the macro. Take a piece type, which should be an identifier, and it will return basically this code. So should be able to, should be able to copy paste that. Like this. And there we go. We also want some extra brackets to make sure all this code is falls under the same match case. So now we can do things like add piece, and of course we have to remember to actually use the input variable here. So here we would add a rook. Here we would add a knight. We would add a bishop and a queen. Don't know why I'm writing apostrophes. If it's a K, we'll add a king. And finally, if it's a P, we will add a pawn. Now, if it's just a number instead, we need to add a number of empty squares. So first we try to parse it in base 10. And if the parsing doesn't succeed, let's start with that case, then we will just fail and make some kind of error message. So this happens if you happen to have like a W or something in this string. But if the parsing succeeds and we get a number, then we want to loop that many times and push empty pieces, empty squares, and increment the position. And that's it. See if I can find the end of this function. Now we simply return the pieces and turn this into a vector. Probably we can change the type here. Just return like that. I think that should be okay. Let's try to run it. And what happened here? Oops. Somehow I forgot an equal sign. This should be lowercase. And now that we are modifying things, the game has to be mutable. And it worked. So we're reading it, but let's try to also print it like we did down here. And as you can see, all the pieces and the squares are seemingly set up correctly. Amazing. Now we just have to handle the few other fields left. So the first field that comes after the position itself is the active color, if I'm not completely mistaken. So let's first get that out using our split on function. We'll split the remainder from before again on a space, and then we simply have to check what this string is. If it's a W, it's white to move. If it's a B, it's black to move. And if it's something else, then we panic. With a nice error message. And I like to put it in quotes so I know exactly what the string was. All right. Then we should read the castling rights. So again, we do the split trick. Actually, just to show what's happening, let's do some printing. So you can see here before it's W, KQ, blah, blah, blah. And then after, we take the string, we split on the first space, and we take the thing before the first space, put it into this variable, and the thing after the first space, and put it into rest. So that's the trick we're using all the time. We'll do it again down here to now split on this space right here, and get the first part, which will be KQ, KQ, and the rest. Maybe there's some nicer way to do this, but I think this is quite a simple and easy to understand way to do it. So now this thing should be a string of some number of characters, maybe none. So we'll start by assuming that there's no castling rights, and then as we loop over the characters in the string, we'll decide whether to add new castling rights or not. Loop over the characters, and depending on what the character is, we'll do different things. So if it's a capital K, then we should add kingside castling for white. So here you see this bit flag thing coming into effect. And this should be, no, it's fine, castling. Maybe if I could type, it would be a little bit easier. And we'll also assume that dash is an allowed character, and then we don't do anything. It just means that there's no castling rights. But if it's anything else, then we panic again. Make a nice error message. So that should do it for the castling rights. Now we'll continue as we've been going and read the remainder of the fields, and let's see what's left at this point. We have a dash and two numbers. So this is the en passant square, and this is the half move clock, and this is the full move number. So as before, we use our split function. Then depending on what we get out, we do different things. So if it's a dash, then there's no en passant allowed. If it's something, then we have to try to get a square from that. But remember that the way we designate squares are by bit strings like this, 64-bit strings. And this S will actually be something like E3. So we need a way to pass that. And we'll write a function called position to bit. We already have bit to position, so it makes sense. And it can fail. So then we will just return the error message. Or it can succeed, in which case we assign to the unpassant field. So let's have a look at this position to bit function. We'll put it up here along with the bit to position. And it should take a string and return a result, which is either a position or an error message. So what does it take for a position string to be valid? Well, one thing is that the length should be 2. So if it's not 2, then we can return an error with the message that it has an invalid length, and the string itself is given by something like this. Okay. Now we have to get out the first character, which is supposed to be a letter, and the second character, which is supposed to be a number, and check that they have valid values. So let's see. The way I do that is just to get a byte array, so I can kind of index into it. Evidently, you kind of need that. So get the first byte, and here we kind of need to know that the A character is a byte with value 97. So we can say that the byte, it should be if it's less than 97, or it's greater than 97 plus 8, greater than or equal to actually, then it's not an A and it's not a B, a C, D, E, F, G, H, in which case it's not a valid column character. Right. And now we can get a column index by just taking the value of the byte minus 97, because if it's 97, it's an A, and cast it to a U32. Now let's handle the second byte and make a row variable. Well, we don't need. Yes, let's make that. So we try to pass it to a digit. Now if it succeeds, then the number should be between 1 and 8 inclusive. So if it's not, then we can return an error. But if it is between 1 and 8, then we simply assign that to, well, we can assign with -1 because we use zero-based indexing, and the notation uses 1-based. So that was if it were passable as a number, but of course, it's hard to see that this case could ever happen because we already checked on the length being 2 of the full string, but let's just keep it now, for now. But if the parsing fails, and we need to return an error again, and it's an invalid row character, I don't have any imagination left, so I'll just put the same error message. So now we have both the column index and the row index. Now we can calculate the number of the square simply as the row times 8 plus the column. And the bit, the bit string version of this is simply bit shift right that many times. And then return an OK value. So that should work. Does not work. What am I doing here? It should be if. And then it complains down here because it has to be a comma. Now it works. So that allowed us to pass also the en passant value. So let's pass the clocks now. And we can actually use type inference here, I guess, is what we're doing. And oops, it's basically the same for the full move. Just do a string replacement. And that should do it. It's running. Let's also now to just, this is not a full test, but just to test it a little bit. Let's print some of the fields. Didn't like that because we need a comma. Didn't like that because this is only debug formatable. Didn't like that. Can we do that? Yes, that works. And as you can see, it got the right values. Of course, this is not a full test of it because we've only tested on one string, but I think this is where we'll stop for now.